if you look at page 7, the tag you have a positively charged solid metal sphere that is isolated in space. The electric field strength E is measured for different distances x from the center of the sphere. The variation with x of the field strength E is as shown in figure 5.1. So the ones that you have here, this one you see they're talking about an isolated metal sphere. So I mentioned to you under electric field there are usually two question types. The first one is for isolated charge. The second one is between two charges. You notice that a lot of questions you have for electric field is either isolated charge or between two charges, and then after that the corresponding graph you get is usually very different. Like for example, for the isolated charge one, when we're talking to you about E versus X, the common graph you see is something like this. Well, when you're talking about between two charges, let's say this is positive, this is charge A, and this is charge B, the graph you commonly see is something that looks like this. Okay, so the graphs are different simply because the situation that they refer to are different. So in your case, this is isolated charge, so by right, you know it should be this one because it is based on the equation E1 over 4 pi epsilon naught Q over R squared. Whereas for this one, between the two charges, the E is actually EA plus with negative EB, giving you a different expression. All right, so back to this one here. Suggest why for values of x less than 4 cm, the electric field strength is 0. So this one I did briefly elaborate on it towards the end of last week's lesson, where I told you that when you're talking about an isolated charge sphere, the keyword here being a sphere, if you have a charge sphere, usually when you want to draw the variation of the field strength with distance, you will notice that your graph for field strength versus distance and potential versus distance will always look like this. So that time what I mentioned to you is that for an isolated charge sphere, if you consider putting a positive test charge to test the field, this one is your isolated charge sphere. You want to test the field, you put a positive test charge here, this one being your test charge, this one being your isolated charge. You can straight away say that these are 2-point charges, so E equals to 1/4 pi epsilon naught Q over R squared, which will give you this graph. You could also say that V is 1/4 pi epsilon naught Q over R, which will then give you this graph. But the thing to always remember is that when you're talking about a charge sphere, a sphere specifically, when you're talking about distances below the surface of the sphere, field strength will always be 0 and potential would always be constant. That is the main thing to understand here. So the thing is that they will always ask you, why is the field strength always 0 inside the sphere? So that time I mentioned to you, your charge sphere is a conductor. It contains free charge carriers. They are constantly moving about. But because they have the same sign of charge, they have a tendency to repel each other away as far away as possible. So they have a tendency to repel each other as far away as possible. They will just go to the surface of the sphere. And then they keep repelling each other until such a point where they stop moving. They reach something like an equilibrium point. They stop moving already. So in that case there, what will happen is that you do not have electric force anymore. No resultant electric force anymore. Okay, so if you refer back to the definition of field strength is Fe over Q, right? If your electric force is 0, obviously your field strength will be 0. So hence your answers looks like this. They will say that for the sphere, the charges in metal don't move. There's no resultant force on the charge, so there is no electric field strength. The question here is asking you to explain why is the field strength 0. So you can say that they don't move, there's no force, so field strength is 0. This is the common answer for that one. Okay, so that part is fine. Then after that, if you were to just move to the next question later on, a point charge of 8.5 times 10 power minus 9 moves from point x equals to 7 to a point where x equals to 5 centimeter. Yeah, hi Naoki. We are at page 7 right now under the electric field chapter. Okay, we're at part B here. You missed part A, but never mind, the lesson is recorded. You can just look at it later. All right, okay, so let's go back to part B. You have a point charge of 8.5 times 10 power minus 9 coulomb that moves from a point where x is equals to 7 centimeter to a point where x is equals to 5 centimeter, right? So use figure 5.1 to estimate the change in electric potential energy of this point, okay? Now, when you're talking about change in electric potential energy, right? They want to change in electric potential energy. I mentioned to you one useful equation to know for change in electric potential energy was this. In your notes, I wrote that I mentioned to you that potential is W over Q, right? Sorry. This one is potential. This one is EPE. So W is QV. So this one is your EPE, and then this one is your potential. If you want to find change in potential energy, delta W is equals to Q delta V. This one here is your change in EPE. Okay, this one here is your potential difference. All right. Yeah, electric field. Now give it an electric field, right? So that time I mentioned to you guys that in your case, your electric potential energy at a point and electric potential at a point can be given by this equation. So this one here is electric potential equals to potential energy per unit charge. So it can be changed to potential energy equals to charge times potential. But this one just gives you value at a point. If you want to find the difference between 2 points, this can be changed to this. All right, the only difference here is that I changed the symbol W to EPE now so that it's easier to see. So here, if I wanted to find the change in electric potential energy, I need to know the charge and I need to know the potential difference between these 2 points, the 7 centimeter and the 5 centimeter point. Okay, I know the charge, which is given by this, but what I'm missing is the difference in potential between the 2 points. But when I want to find the difference in potential between the 2 points, you have a problem here because your graph is not potential versus distance. If you look carefully, this is field strength versus distance. What I get from here and what I get from here is not going to be field strength. Sorry, it's not going to be potential. It's actually field strength. So how do I find the value of potential here from the graph? Okay, now this one is not inside your notes. I didn't write this inside your notes, but it's applicable in your exam. What they want you to realize here is this. You see, if I tell you E at a point is equals to E 1 over 4 pi epsilon naught Q over x squared, and I tell you that V at a point is equals to B 1/4 pi epsilon naught Q over x. I change the R to x here. You can just leave it at R if you want to. Now this one here, if I modify a little, E is 1/4 pi epsilon naught Q x squared. Oh yeah, sorry, maybe I don't modify from here. Yeah, let's say I modify from something else. I modify from v, sorry. Say if I look at this one, I want to modify from v. V is 145 epsilon naught x, right? If say I multiply with x over x, this one will give me v is 1 over 4 pi epsilon naught q over x squared times with x. Now me multiplying with x over x here actually doesn't change the expression for v, because x over x is actually equals to 1 in the first place. So me multiplying with x over x here actually doesn't do anything to the original equation. But what it does is that it changes it to another form. It changes it to another form. This x multiplied with x will give you x squared. This x and leave it here, you'll get this. Now this one here, you see 1 over 4 pi epsilon naught q over x squared is actually my value of e. So from here, I can come to that conclusion that my v is ex. Okay, my potential at a point, other than using this equation to find potential at a point, I can also use this equation. All right, potential at the point could also be the field strength at that point multiplied by the distance at that point. Okay, so this part here, I don't think I written it inside your summarized notes, neither have I written it inside your notes itself. Maybe you want to just jot it down somewhere just in case. All right, the way of doing the questions using this equation, I mean for questions that make use of this, is very, very rare. I think there's only 2 or 3 questions so far that makes use of this in order to find the answer. So it is rare to see this, but in the event that you encounter it, just know that to find potential at the point, it is field strength multiplied by the distance, because it's derived from here. All right, so as I mentioned to you, you may not be able to find out the value of v or potential directly from your graph, but you can find out the value of the field strength, isn't it? So what you want to do is that if you have the value of x, you'll be able to find the value of e. The E1, X1 here gives you the value of potential at this point. If you're talking about 7 centimeter, this is the corresponding value of field strength, right? The E2, X2 here will give you the value of V2. So now you will have the values of potential at this point and this point. So if you find the difference, you multiply with your charge, you'll be able to find out your change in electric potential energy. Okay, so that's why your workings here was written as this. For point charge, maybe this one, yeah, for point charge, V is equals to EX. Maybe I need to write this. For point charge, okay, potential at a point, yeah, maybe it's better not to write for point charge. Maybe this one you would be better off saying that potential at a point V is equals to EX. Then after that, you find the difference in the potentials. You find the values of potential at the 2 different locations, 7 centimeter and 5 centimeter. Then after that, you multiply, and then after that, you multiply by the charge. You will get the energy involved. Right? So that one is one part here. Okay, that one was actually page 7. Then after that, the other one that I can go through with you is page 16. All right. So If you guys are okay with this, then I'll just go on to page 16. All right. Okay, so if you're okay with this, we will just have a look at page 16. Just look at page 16. Okay, so electric field and capacitance chapter, page 16. Okay, so just have a look at page 16. Okay, now this one is two solid metal spheres A and B have equal radii and are in vacuum. The centers are 15 centimeter apart. Sphere A has a charge of 3 picocoulomb and sphere B has a charge of 12 picocoulomb. The arrangement is illustrated in figure 5.1. Point P lies on the line joining the centers of the sphere and is a distance of 5 centimeter from the centers or from the center of sphere A. Suggests why the electric field strength in both spheres is 0. Okay, so for your case here, you see this question here concerns between two charges. As I mentioned earlier, usually electric field questions only has two kinds. The first one is where they just talk about a single isolated charge. The second one is where they talk about between two charges. All right, the graphs that you will get is going to be different. The equations that you use will be different. All right, as you will see here later. Okay, so now for your case, they're just asking you, why is it that for the charge spheres here, the electric field strength inside is going to be 0? So you could generally use back that same answer. As I mentioned to you last week, for charge spheres, your charges no longer move. When they don't move, there's no force. When there's no force, there's no field strength. So let me just show it to you. Yeah. You could use back the answers from the previous question under page 7. This is the answer from your previous question. You say that the charges in metal sphere don't move. There's no resultant force on the charge, so there's no electric field. The reasoning is because E is Fe over Q. If this one is 0, obviously this one is going to be 0. The other answers that your marking scheme puts here is this. They tell you here in electric field, charges will move. For the sphere, there's no movement of charge. So the field strength is 0. Okay. In electric field, the charges in sphere will move due to force. For the sphere, there's no movement of charge. So no force. So no force, therefore field strength is 0. If you read this in itself, it doesn't seem complete because they didn't tell you certain things inside. In an electric field, charges in conductor will move because there's the presence of electric force. For the sphere itself, the charges don't move. So this tells you there's no force. So when there's no force, the field strength is 0. Again, it will imply back this one. So if anything, this one is actually a better answer. This one is trying to tell you more things, but they miss out certain things in the middle. All right. So you can have a look at that. Just take a minute or so to copy it if you want to. Okay. Then if you're okay with that, then you just go on to another different way, another different question. If you look at part B, show that the electric field strength is 0 at point P. Explain your working. So in your case, we are asking you right now to show us the field strength at point P is 0. Okay, explain your working. So usually when that time when I talk to you about the case for between 2-point charges, I mentioned to you sphere A would have its own electric field, sphere B would also have its own electric field, but the moment you place them close to each other, their field strengths would overlap and give you the field would overlap and give you another new resultant electric field. So when you're trying to test the region between the two charges, whatever property you have here, whatever property or quantity of your electric field that you have here is actually due to the combined effects of A and B. So that time I subsequently mentioned to you, you need to consider the effects due to each sphere individually before you add them out to find out what's the resultant. So in my case here, I usually would use a positive test charge to test the field. Say in a point P here, I go and put my positive test charge here. Sphere A is positive. What will be the direction of force acting on the test charge here? It will be towards the right, isn't it? And likewise, your electric field strength due to A will also be towards the right. So EA will be towards the right. Sphere B is also positive. This is positive, this is positive. The force on the test charge here would be towards the left. So the field strength due to B will also be to the left. So in my case, the field strength at P is actually EA plus with negative EB. Why this one negative? Is because opposite direction. Alright, so what you can do now is you just do something like this, where you find out the potential at point P, find out the potentials due to A, find out the potentials due to B, and then after that you just say that the fields are opposite in direction, therefore E is 0. This one is just one way of doing it now. Because you see that the question says this part here, explain your working. Alright, if you wanted to do it like this, EP is equals to EA plus EB, you can do it too, but you just need to write this statement. Wait, let me just get rid of this. The ones that you see being written here is just you finding the magnitude of the field strength due to A and B. And then after that, you explain further saying that the fields are actually acting in opposite direction. So they add up to 0. That is what this question is, the working here is trying to tell you. You show them what is the magnitude due to A, sphere A, what's the magnitude due to sphere B, and then you have to explain that both of them are actually in opposite directions. So they add up to 0. Okay. If you wanted to do it like this, just straight away add up to show it's 0, you can also. This one you will just have to say that EA and EB are acting in opposite directions, therefore EP is EA plus with negative EB, so you get 1 over 4 pi epsilon naught QA over XA square minus 1 over 4 pi epsilon naught QB over XB square. So in your case here, if you do it like this, you will eventually get back the answer as 0. Also can be used. The explain your working part here, strictly speaking, just wants you to say this. They want you to specifically point out that EA and EB are in opposite directions. Alright, so you can either do it this way or you can either do it this way. Personally, I prefer this way lah. But this one is I just follow from the marking scheme last time when I look at it. Alright. Okay, so if you're okay with that, then we just move on. Oh yeah, before I go to that, if you're wondering what is your XA, XB, you need to be careful a bit about your XA, XB. Now this one you will know is your QA. This one you know it will be your QB. Your XA is this one. Okay, this is your XA. This one is your XB. Okay, XA is the distance between charge A to the point that you're considering. XB is the distance between your charge B to the point that you're considering. they are different values. XA will be 5, XB will be 10 centimeter. All right. So you just submit your values accordingly and you get your answer. And usually now you want to make your working a lot simpler and a lot cleaner. Your 1/4 pi epsilon naught, you can just straight away substitute with 8.89 times 10 power 9 because the values are already given in the first page of your data sheet. Yeah, this one, you can save up more time now rather than following like what I did, manual calculating 1/4 pi epsilon naught individually. This is actually wasting time. You can just straight away say 1/4 pi epsilon naught is 8.89 times 10 power 9. You make your workings a lot cleaner also. Okay, so this part is okay. Then after that, they ask you calculate the electric potential at point P. All right. So if you're okay with this, I think you guys should be okay with this. So let me just erase all certain things. Right. Let me just erase all certain things. Okay, so this one you are okay. Then you move to part C, where they ask you calculate the electric potential at point P. The first question asks you to find the electric field strength. The second question asks you to find out the electric potential. Okay, so when you want to find out the electric potential, you again do the similar analysis. You need to find out what is the potential due to sphere A and potential due to sphere B. Okay, so just now I told you, you wanted to find out what is your field strength here. You need to consider separately the effects due to sphere A and B. Let me just, I can't put this one in. Okay, right. Okay, so this one was you finding electric potential, electric field strength. Now you want to find out your electric potential. You need to find out what is your, you want to find out your electric potential at this point. You need to find out what's the electric potential due to A and electric potential due to B. So in your case here, you will have VA here. You will have VA here, and then you have VB here. Now this one, your sphere A is positive, so your VA is positive. Your VB is positive. Your sphere B is positively charged, so your VB is going to be positive. So your VP is going to be VA plus VP. Okay. Your VP is going to be VA plus with VB. All right. In your case here, VA has no direction. Positive and negative is determined by the sign of the charge. EA is your field strength has direction. So positive and negative is determined by the direction. Okay, now maybe I better just write it out for you. E is vector, positive or negative is determined by direction. Okay, is determined by direction. Okay, then we'll tell you V is scalar, positive or negative is determined by sign of main charge. Okay, so this one will make things clear for you. All right, when you're talking about field strengths, any positive and negative is just strictly speaking determined by the direction. It would have direction. Vector has direction to consider. All right, but when you're talking about scalars, scalars have no direction. But positive and negative here is determined by the sign of your main charge. All right, so that's the easiest way I can just explain it to you. Right, this one has direction, this one has no direction. Okay, so in your case here, whatever positive and negative you have here is just strictly speaking determined by the sign of your main charge. VA, the main charge is A, so it's positive, this one is positive. VB, the main charge is B. If this one is B positive, this one will be positive too. Okay, so at point P, your potential is VA plus VB, which is actually just simply this one, 1 over 4 pi epsilon naught QA over XA plus with 1 over 4 pi epsilon naught QB over XB. So I explained to you XA, XB already just now, or RA, RB lah. Alright. So you just sub in your values, eventually you get your electric potential as 1.62 volts. Okay, so that part should be it. Okay, so yeah, this one here you see I use 1/4 pi epsilon naught. I straight away use it as 8.99 times 10 power 9. It will be much faster to use this value straight rather than subbing in the values one by one. All right, so you get your value of electric potential as 1.62 volts. So if you're okay with this, then I move on to the other part of your question, which is basically this one. All right, so I'll just clear off this drawing. All right, you can find it in the video recordings later on. All right, now you have a silver nucleus argentum 107 that has speed v when it's a long distance from point P. Use your answer in C to calculate the minimum value of speed v such that the nucleus can reach point P. Now, usually when you see those kind of questions where they ask you, they tell you they're launching something and then they ask you to find out the minimum speed such that the thing can reach a certain point, usually that means find out the speed you need to launch it so that by the time it reaches the point, the speed is 0. Okay, what I mean by that is, I think it's better to see from this diagram here. All right, or maybe I better just redraw it for you. They tell you you have an argentum nucleus that is moving with speed v a long distance away from point P. Okay, the few things here that you need to be aware of is that when they say this one is long distance away from point P, this one is assumed to be from infinity. Okay, and then just now as I mentioned to you, the minimum value of speed v such that the nucleus can reach point P, this one means that by the time it reaches point P, the speed should be 0. That's the significance of these two statements here. So if I talk to you about point P, you refer back to what point P was just now. Point P was actually between sphere A and sphere B, right? You have sphere A here, and then you have sphere B here, and then after that, this one is basically that point P here, all right? So this is that point there, point P here. You have your argentum nucleus that you're launching from infinity towards point P. All right, a long distance away from point P means it's from infinity. So you have your argentum nucleus like this, moving with speed v, and it is moving from infinity. Okay, then after that, just now we mentioned to you that if you are talking about minimum value of speed v such that it can reach point P, that means by the time it reaches here, this one will be 0 meter per second. Okay, so you see here, this one is speed v meter per second. This one is 0 meter per second. Okay, now there's also another thing here that you need to know. At infinity, your potential is 0, isn't it? Okay, your potential at infinity is 0, but your potential here is 1.62 volts, which you already found just now in the previous question. Okay, so now if I talk to you about a case where you're moving from here to here, when you move from here to here, what you will see is that by right, from V meter per second to 0 meter per second, that means you are slowing down, right? Okay, you're slowing down, so your KE should be dropping, which you can clearly see from here. This is V meter per second, this is 0. You're slowing down, your KE should be dropping. According to conservation of energy, your EPE instead should be increasing. Okay, so here what you could say is that whatever change in KE you have will be the same as the change in EPE that you have. Okay, now would it be logical to say that your KE here is dropping, you are slowing down? It is actually logical to think it that way, because you see, we told you that you're launching an argentum nucleus. You see, you're talking about an argentum nucleus. We're talking about nucleus, not atom. Nucleus is positively charged. So your argentum nucleus is positively charged. Remember just now when you're talking about sphere A and sphere B, they were also positively charged. So you have a positive charge moving towards another region where you have positive charges. So when this positive charge moves towards here, it's going to experience repulsion, isn't it? The positive charges here will try to repel this positive charge from moving towards them, right? So because you experience this repulsion, obviously you will slow down, which is consistent with what you see here. Okay, and then at the same time, your positive charge is moving towards a region with positive charges, your electric potential energy will definitely increase also. So it's also consistent with what you see here. So this is logical. All right. So that one is just further information for your knowledge, but it's just enough for you to see that here to here, KE is dropping, EPE should be increasing. But as to why, it's actually based on what I just explained to you. All right. This one dropped because speed is dropping due to repulsion from spheres A and B. This one EPE is increasing because positive charge is moving towards other positive charges. Okay, this could be another way of explaining why is it KE is dropping, EPE is increasing. Okay, speed is dropping due to repulsion from sphere A and B, therefore KE drop. This one EP is increasing because positive charge is moving towards other positive charges, so it becomes even more repulsive. So your EP definitely is increasing. Okay, but enough of that. So we go to this one. I talked to you about change in K equals to change in EPE. So in your case here, your KE here would be half mv squared. Your KE here obviously would be 0. Right, your EPE here. Now, EPE, I mentioned to you, is useful to use this. Change in EPE between 2 points is actually the charge multiplied by the potential difference. Okay, this is difference in potential. Okay, so this one, change in K is half mv squared minus 0. And then change in EPE is actually Q times delta V. Delta V here being my difference in potential, which is just 1.62. All right. Yeah, your other thing here I need to mention is that for changes in energy, always take larger value minus lower value. Okay, you don't need to be so fixated on whether it should be initial minus final or final minus initial or the other way around, or whether should you maintain it on the left side and right side. Don't bother about that. Whenever you're talking about changes in energies, you always just take the larger minus the lower value. All right, because you're just interested in the magnitude. All right, so just take whichever is larger minus the lower. Okay. So like in my case here, change in potential, I will always just take the larger minus on the lower one, which is 1.62 minus 0. Okay, so it's just 1.62. For change in KE, take larger minus the lower one is just half mv squared minus 0. Okay, so you get this expression here, which eventually tells you that Q, which eventually tells you that speed is actually Q times delta V. Sorry, V squared is actually 2Q delta V times 2Q delta V over M. Now, this one here is where you need to be a bit careful again. This one refers to the argentum nucleus AG47107. All right. The charge of your argentum nucleus will be provided by your proton, which is 47e. The mass of your argentum nucleus will be based on your nuclear number, which is 107u. Okay? That's why your charge here is 47, 1.6 times 10 power minus 19. Your mass here is 107 times 1.66 times 10 power minus 27. So eventually you get your speed as 1.17 times 10 power 4 meter per second. Right? Okay, so if this one is fine, then I continue on with the others. Right. Right. Okay, so this one fine now. Then I move on to page 18. I'll just move on to page 18. Okay. Page 18 is again between two charged spheres, but this one they talk about field strength and potential again. Right, so if no issues here, we move on to page 18. Okay, so I'll just clear this one off. Now, two solid metal spheres A and B each have radius of 1.5 centimeters situated in a vacuum. The centers are separated by a distance of 220 centimeters as shown. Both spheres are positively charged. Point P lies on the line joining the centers of the two spheres and the distance x from the centers of sphere A. The direction with distance x of the field strength at point P is as shown here. Okay, so again, when you look at this question, you see that there are two charges here. You know that they're talking about a case between two charges. All right, your question here is for between two charges, not an isolated charge. All right, so here they gave you the graph of field strength versus distance. This one is referring to the field strength between the two charges here, which is taken from this equation. So that time I mentioned to you, if I wanted to find the electric field strength at any point here, I put a positive test charge. If this is positive, this is positive, EA is this side, EB is this side, but field strength is going to be EA plus with negative EB. Negative because it's in opposite direction. So I got 1/4 pi epsilon naught QA over XA square plus, sorry, not plus. Then I get minus 1 over 4 pi epsilon naught QB over XB squared. So I change the values of x. I'll be changing the values of XA and XB. Eventually, I get this graph. Okay, this is how I got this graph in the first place. This is talking to you about the resultant electric field strength between these two charges. Okay, how they got this shape was based on this equation after they consider the effects of both spheres. All right, and also you'll notice that this one here, when they drew it, inside the sphere itself, they indicated to you your field strength is 0, consistent with what you just learned. Anytime you talk about inside your sphere, your field strength must be 0. Okay, Right. So now they ask you use figure 6.2 to determine the magnitude, sorry, the ratio of magnitude of charge on sphere A to magnitude of charge on sphere B. Okay, the ratio of charge A to charge B by using this figure. All right. Now the easy way to look at it would be you try to find out from your graph where is your point 0. Wait, now let me just show you the answer. This is question 6. Okay, they ask you to find out the ratio of magnitude of charge on sphere A to magnitude of charge on sphere B. Now, all you just need to know, if you wanted to, you know that the resulting electric field strength at any point here is given by this equation. You want to find the ratio of QA to QB. Now, it will make your workings a lot faster if you are able to find out the point where E is 0. Because if this is 0, eventually you get this 1/4 pi epsilon naught QA over XA square equals to 1/4 pi epsilon naught QB equal over XB square. Cancel off, then you get this. You'll be able to find out what is ratio of QA to QB straight. So for this question here, when they ask you to find the ratio, what you really want to find is the point where E net is 0. The here is E net, I wrote here is E net. This one is already the E net itself. This is the resulting electric field strength between the 2 points. You purposely single out the point where your electric field strength is 0 so that you can simplify this equation to this. And then from there, you'll be able to find out what is the ratio of your distances, the ratio of your charges. Okay, all you just need to say is this now: at x equals to 11, the E net is 0, so EA will be equals to EB at that point, because you can see from here. Then you can simplify to this. All right, this one is basically this. E net is equals to this. When E is 0, EA equals to EB. That's what this one means. All right, the workings. You could write it as this now. E is EA plus negative EB. When E is 0, EA is equals to EB. Then after you can start subbing in already. You can also work it like that if this one makes more sense to you. All right. But the gist is that you need to make reference to the part where field strength is 0. You must show it in your working somewhere. So in your case, you could write this. E is EA plus negative EB. When E is 0, EA is equals to EB. Then after you can further say that E equals to 0 when X equals to 11 centimeter. Then you can start working at this already. Right. You can start working at this already. From here, I think you have to do it like this. No? When E is 0, EA equals EB. E is 0 when X equals to 11 centimeters. So you get this. Yeah, then you sub it in. Yeah, this one here, you can actually have to do something else to it. Your distance X here is not XA, XB. Not strictly speaking XA, XB. Your X here is measured from the center of your sphere A. Okay. X A can be said as being equals to X. All right. But XB is actually your value of 20 centimeter. Sorry. It's actually 0.2 minus X. What I mean by that is this one. If you look at your diagram, this is the point you're considering. This one is XA. This one is XB. It's actually the total length minus X. Total length minus X itself. Or minus XA. Okay. So just be careful about your length. At 11 centimeter, which is somewhere around here, this one will be your XA, and then this one will be your XP. Okay. Wait, let me just get it out. Right. So XA is from here to here, XP is from here to here. XA is actually your A. XA is actually your X itself. XP is actually your 0.2 minus of your X or your XA. So your workings will look like this. Alright. Okay, the workings here I did not change to meter. I left it in centimeter because the units will cancel off. Right, you can leave it in centimeter, you can leave it in meter if you like. They will cancel off eventually. So it doesn't really matter. Right, so you eventually get your ratio as 1.49. Right, QA to QB is 1.49. Okay, so if this one is fine, then I'll just clear this off. Okay. Right. Is there anything else here that I needed to change? Yeah, nothing here to change. X I mentioned to you is X. XP is actually 0.2 minus X. Yeah. Okay, so you just you just follow the workings here and you should be fine. Now, the next one that I need to mention to you is your part B, where they tell you that the variation with distance x of the vector potential V at point P is as shown here. So again, this graph is obtained by you finding the potentials due to A and potentials due to B and adding them out. So VP is VA plus VB. If I want to find out potential due to A, it will be VA. Potential due to B, it will be VB. But potentials being scalar, they have no direction. That's why there's no error here. No arrows here. But it doesn't mean that they do not have positive, negative. Any positive, negative is strictly speaking dependent on the sign of the main charge. If this one was positive, this one will be positive. If this one is positive, this is going to be positive. So VP is just VA plus VB, okay, which in turn gives you this graph here. So again, here you can see that thing here where when you're talking about distances inside the sphere, your potential is constant. You can see it here, you can also see it here. All right, this is them drawing it out to reflect the actual situation now. Right, so this part is okay, don't worry about that. They're not asking you to calculate anything here. This is just to explain to you how they got this shape. It is based on VP equals to VA plus VB. Now here they tell you you have an alpha particle that is initially at rest on the surface of sphere A. The alpha particle moves along the line joining the centers of the two spheres. For the alpha particle, as it moves between the two spheres, find out its maximum speed. Okay, find out its maximum speed. Okay, now when you look at this graph here, there are actually a few ways in which you can do this. I think the easiest way for me to explain this to you is by looking at the changes in energy. I won't explain in terms of force. I'll just explain in terms of energy for you here first. You see, your graph looks like this, right? This is a graph of potential versus distance, where we tell you it looks like this right now. Okay. The question wants you to find out the maximum speed of the sphere. Now, common sense will tell you the maximum speed should be here. This is where you are going to get your maximum speed. Okay. But if say you wanted to double confirm, is it really the maximum speed? The easiest way I can tell you to do that is to look at how the graph changes. Now, this is potential. But potential is very closely related to EPE. Okay, you can say it's actually proportional to your EPE, right? It's actually proportional to your EPE. All right. So look at how the graph changes. In your case here, you see if I move from here to here, my EPE is dropping, my KE is increasing. But then when I move from here to here, my EPE is increasing, but my KE is dropping. So it implies to me that from here to here, because from here to here, my K is increasing, I am speeding up. But then from here to here, after that, my K starts to drop. After this point, my K starts to drop. Here, I start to slow down. So this must be the point where I have maximum speed, because here is where I stop speeding up. I start to slow down already. So I would say that this part here is maximum speed. Okay, just by looking at the graph like this itself. No need to talk so much about the force now. There's another explanation based on force, but that one will be a separate question. But this one I show you how to look at it in terms of energy itself. Okay, so your maximum speed you understand would be somewhere here. All right, so you apply principle of conservation of energy for this part only. Okay, this one here, you apply principle of conservation of energy, you will say that any change in your KE will be equivalent to the change in your EPE. So in your case here, this one here, your change in KE will be equals to change in EPE. It will be half mv squared minus 0. Now, how do I know that this one will be your max speed V, right? Let me get this out first. This part here will be your max speed V. This part here, when you start moving, your V is 0 meter per second. How do I know you're at 0 meter per second here? Is because they tell you your alpha particle was initially at rest on the surface of sphere A. So it's 0 meter per second. Then it started moving, it reached maximum speed here. So this point to this point, your change in Ka is half mv squared minus 0 only. And also I mentioned to you just now, changes in EPE is equals to Q times change in potential. You already know the potential difference here. You know the potential here, you know the potential here. You can work out what is the potential difference. So you can find the change in EPE, right? So eventually you can get this. Because this is alpha particle, helium-42, the mass of alpha particle is 4U. The charge of alpha particle is 2e. So that's why your mass here is 4 times 1.66 times 10 power minus 27. And there's also the reason why your charge here is 2 times 1.6 times 10 power minus 19. Right? Okay, so you get the answer as V is 7.4 times 10 power 3 meter per second. Then you get your answer already. And from there should be fine. Okay. Right, then after that, if you were just to look at the other parts here, below here, where we ask you this. Okay, now find out the speed on reaching the surface of sphere B. This one is asking you to find out the speed on reaching the surface of sphere B. Now there are two ways to go about this question, depending on what you're inclined with. I'll just explain both methods to you in your current case here. Okay. Now your graph originally looked like this. Your graph originally looked like this. This is how it looked like just now. Now they want you to find the speed on reaching the surface of sphere B. This one was basically sphere A just now. This one is your sphere B. They want to find out what is the speed here when your alpha particle was launched from here to here. What is the speed on reaching the surface of sphere B? Now, in your case here, you actually have two ways of going about this. You can actually consider just the energy change from here to here. This one here, you see that your EPE, this one is your V versus F. This one here is your EPE dropping. Your KE is increasing. Or you could also consider it from here to here. This one, your EPE is increasing, but your KE is dropping. Now, whether you use this method here or this method here, you will still use change in KE equals to change in EPE. But the only difference here is what you will use for your V and what will be your change in KE here. Now, if I look at this working here, change in KE equals to change in EPE. This one is based on this one. This is the first method. All right. Here I know it's 0 meter per second, so my KE is 0. Here is V, unknown value of V, so my KE here is half mv square. So in my case, I will consider this one and this one. Change in KE is half mv square minus 0. My Q, then my change in electric potential energy is Q times change in Q times the potential difference. My potential difference being only this one. This one would be my potential difference from this point to this point. It will be 0.76 minus 0.4 giving me 0.22. And then I just replicate back the same values of mass and charge from the previous question. I'll get the speed as this. Okay. But if, say, for example, I wanted to use the second one, this one being my second method of doing the question, I will still say it's change in KE equals to change in EPE. But in my case here, you have to realize that your V here is not 0. It's a non-zero value. This one here is actually your V max at this point here. So when you're talking about your change in KE, it will actually be half mv max square minus half mv square. Then it goes to Q delta V. Alright, so you see the biggest difference here will be in the change in KE. If I'm using this one here, I do not have a 0. It's actually half mv max square minus half mv square. But this one here, because I'm considering from here to here, one of the values will be 0. That's why it's like this. But this one here, when I consider it this way, it won't be 0. Okay, so that is one of the biggest difference in your method here. So this one here, you need to be careful of it. Alright, and then another thing here will be on your delta V. Your delta V, if you're using this method, the method 2 here, your delta V will actually be this one. This one would actually be your delta V. Okay, so for this one, your delta V is this one. It is here. But if you're using the first method, your delta V is here. Okay, so there are different values. But you will still get back the same answer. Alright, doesn't matter whether you're using method 1, doesn't matter whether you're using method 2, you will actually still get back the same answer. It depends on your preference actually. Alright.